Okay. All right. So for you guys, just a couple of reminders about some things. As you know, each week you guys have your semester complete outline of what's happening. So this week, the plan is to do a couple of topics. It's actually quite a nice week this week. All right, we're going to be finishing off this topic, Unit 4, Topic 1, okay, of integration. All right, so we're going to be looking at what we call volumes of solids of revolution. Doesn't mean much until you see it. And then we're going to do Simpson's rule, which is basically very similar to the trapezoidal rule that we did in methods, just a slightly different formula, but the processes are exactly the same. Okay, so that's what we're going to do that. So we're going to start with volumes of solids today, and then in the double tomorrow I'll give you some problems to work out, and if we get a chance we'll start Simpson's rule, otherwise that'll be Wednesday. And then Friday, as always, is our catch-up lesson. Continuing to provide revision, okay? So what I've got so far is I've put out a couple more practice topics for you to start revising. So a little bit of revision about topics for vectors, okay? So these are specifically about, so review the concept of vectors from Unit 1. So we spent a fair bit of time doing that. We looked at things like dot products. We looked at things like position vectors. We looked at cross products, okay, all with 2 dimensions, and then extend them to 3 dimensions by looking at the unit vector k, which is obviously along the z-axis. So we had I on the x-axis, j on the y-axis, z on the k-axis, and also the idea of altitude, okay, so phi. And there are some questions to have a go at here. All right, so there's quite a few questions there, and then some other questions about that topic, which is proving geometric results in the plane and construct simple proofs in 3 dimensions. So there's a 2-dimensional one here, okay, and then there's a couple of 3-dimensional ones. Okay, now okay, so is that there or up there?
Yeah,
Next door.
I love the great hands being here.
That's great. Okay, so just a reminder, just like it was, I'm more doing this for our colleagues online, but so the answers to those 2 are up in here. So the idea, what I've tried to do with the answers is these are the solutions to how to do those. Okay, and so they're there for you to do as you choose. Okay, so as promised, what we're going to be doing today is not that, nor that, nor that, nor that. There we go. So what we're going to be doing is this concept of a volume of a solid of revolution. So the best way I thought to demonstrate this was steel. So I found this is a really, really useful little tool to illustrate what it is that we're going to be trying to achieve when it comes to volumes of solids of revolution. So what we've done so far is we've been able to calculate area under curve. Okay, so this graph that I've got up here is the square root function, so y equals root x. Okay, and it's to a particular value which we don't need to worry about. All right, and we could find quite quickly and easily the area under that curve. Okay, and so if we were going to find the area under that curve, so let's say that I wanted to find the area, I can't write on the screen, so let's say that I was going to find the area between 0 and 2. How would you do that? Integrate it. Yep, so you just integrate it, sub in 0 and 2 and solve. Pretty simple, right? So we can find the area. But what we can also do, and so if we start rotating that, so this is an example of rotating it around the x-axis. So that might look like it's just bouncing up and down, but we can also, if I rotate that towards you, okay, all right, it still looks like it's just bouncing up and down, so I'll just move it back to there. Now if I was to carve that out, so if you imagine it like a lathe, okay, then I can actually carve out solid, okay? And so if I was to rotate that solid now, okay, you can see that in this particular case it creates that sort of that shape. Pretty cool. All right. And what we're going to be learning to do is work out, well, how do I, and I can rotate that so we can see the front of it. Just get it straight. There we go. So we're looking at front on, we can see that it's a circle, but it obviously decreases in size. Okay, so the idea that it's a circle is really important, and that would make sense. If you have a solid and you rotate it around, either, in this case we're rotating it around the x-axis. Okay, and so if we're rotating around the x-axis, we end up with a circular shape, at least as the base. Right, so if we think about the formula, what shape, what do we call? Well, we're creating kind of a prism, kind of. Okay, we're kind of creating it's more like a pyramid, I guess, but it's in that sort of ballpark. Okay, now, in order to calculate, the problem with calculating the volume of that shape is that, well, we've got a curve here. Okay, so how do we overcome problems with curves? We use calculus. Okay, so I'll just stop that rotating for the moment. Now, how did we come across the area formula for integration? Can everyone remember back to when we first looked at areas and we were deciding how we were going to introduce them? How do we justify the solution? Or how do we justify that the integral is accurate? So I'm just going to come across here a bit so I've got some space. Can anyone remember? Sort of, yeah. Well, okay, so if we think about the trapezoidal rule is just one example of how we can calculate that area. But what did we do? So if we have the function where we've got y equals root x, all right, so we've got y equals root x, and if I wanted to find the area under that, we now know that we can integrate root x with respect to x between, so let's just go a to b, right? So we can integrate between a and b, and we get the area. We know that. But how do we come across, what do we have to do to get to that point? So what does this symbol actually mean?
Infinite increments between A and B?
Yeah, but what about them? Yeah, there's infinite increments between A and B, yes, but what are we going to, in order to find the area, what have we done with them? No. So to find the area, what we did was we split this up into smaller and smaller sections, right? So if we think about that area there, well, that was delta x. Okay, so we looked at differences in x's, and then we multiplied that by the height, and that gave us our area. Okay, and for the trapezoidal rule, for example, or Riemann sums of rectangles, or whichever method you want to do, that's what we're basically doing, is we're taking our little tiny strips of area and adding them up. And so this symbol has developed from the summation symbol, right? Because it's sigma, capital S, right? Looks like a big S. It's a coincidence? Think not, right? So basically, in order to come up with this idea of an integral, is we took really, really small values of x, hence the dx part here, right? So we've got the heights, which is basically just substituting the x value into our function, right? So substituting the x value into our function, multiplying it by the width, and then adding them up. And that gives us our area. And if we can make this delta x approach 0, then that's how we get our integral. We make those widths as small as we physically possibly can. And that's how we go from the sum of our function between, like, I guess n equals 0 to b, or a to b, sorry. Okay, multiplied by our delta x, so the heights, multiplied by that will give us our area. Make sense? And then we just use calculus to go to that. Okay, and that's where, so our small deltas, if we make them infinitely small, we end up with that, the dx part. Okay, because that's where we did the same thing for derivatives earlier on when we looked at gradients. Okay, the function itself is, well, if you substitute values, any value of x into our function, that tells us the y value. Therefore, that's the height. Width times height is area. Okay, So what I'm trying to get to there is we can do the same thing. Just find the function, there it is. We can do the same thing for volume. Okay, so what we can do is we can then make a whole heap of cylinders. Okay, so now we've got a 3D shape of a whole rack of cylinders, and you can sort of see the little cylinders there. Okay, and once again, as I got to remember where this is, there it is. So therefore there's the situation where we've got 10 cylinders. So we could find the area of each cylinder, right? Oh, sorry, the volume, my apologies, the volume of each cylinder. And then we can just find the volume of that one, and the volume of that one, the volume of that one, and add them up, and then we've got the approximation of the volume. Just like we did for area, right? So how do I make that approximation more accurate? No?
Well, you just get the equation for a cylinder and
Yeah. But if I was looking, yes, that's where we're going. So just take one step back, right? So I'm going to use cylinders, 100%. I'm not going to make them trapezoids or anything because trapezoidal, no. We're just going to keep cylinders, right? Because cylinders we can find the area times height, right? Area is a circle. So what's the radius of this circle? It's whatever I substitute the x value into that y value, don't I? Just like, so the radius is basically the same as what we had for the area, but it's two directions. So if this value is like 5, and if I want to know the radius, right, it's going to be root 5. So I'd sub it in. Okay? And the area of a circle is pi times the radius squared. Right? So it's going to be pi times the y value squared times the height, which is that delta x like we had before. Yeah? And that will give me the volume of that strip. And then I can do the same thing for that strip. And then I can do the same thing for that strip. And I can add them all up. So you can see can you see where this is going? So if I want to make that approximation more accurate, what do I need to do?
You take the equation for a cylinder.
No, before that again. Just something even simpler than that. What did I do? What would, if I went back to...
Make the width smaller.
Yeah, I make more cylinders. Because as I increase the number of cylinders, can you see what's going on up here? Right? As I get more and more and more and more cylinders, and this only goes up to 20, I could increase it, but I couldn't be bothered. Right? So as I get more and more and more, and closer and closer and closer, where the width is closer and closer to 0, my volume is going to be closer and closer and closer to the actual volume rather than approximation. So then, right, finally got there, Adam, we got there. Then I can just create, instead of having a delta x, I can make it dx. I can make the sum into an integral sign. Okay? And then we can create our volumes from that. Okay, and I can rotate that back and forth if I want to. And I can make it really bad, right, with 3 and so on. Okay? So I can turn that off. Okay? And so we've got our cylindrical, I'll turn that off for the moment. Don't want to do that? No, it doesn't really matter, I guess. Yeah, and so we can end up with our solid of revolution. Okay? So does that make sense? So this is where the formulas that we're going to work with today have come from. It's just taking our idea of area and making it three-dimensional. Okay? So let's come back to here. So if we're looking at, first of all, we're talking about rotating around the x-axis. So this is the mathematical derivation of what we just talked about. Okay? So we've got a situation where we've got any old function that we want. Okay? So we've got y equals f of x. Now, I had the root x function before just to graph something, right? But it doesn't actually matter which function you've got. So let's say we want to find the volume of rotation around the x-axis. So basically what that means is I'm going to take that blue shape there and just rotate it. And then you end up with that shape there. Right? So we end up with this shape there. So you look at your endpoints. Okay? So effectively what I'm going to have is, well, I've got circles. We talked about that already. It creates a circle at the end, so we know the pi r squared idea. Okay, so the volume we know is the area multiplied by the height, because they're prisms. Okay, well the area is a circle, so it's going to be pi multiplied by the radius squared multiplied by the height will give me my volume. Okay, so what we're working towards is, okay, well pi is pi, so it's not going to change anything, so we'll just leave it where it is. Okay, the radius, well, this is what we have to work out. We'll come back to that in a second, but we'll get to that idea. And then we've got the height. So the radius is going to be, well, I can do it right now, I guess, is going to be the function at the x value that I'm interested in. Right? So if I'm at this point here, let's say b was 5, then I substitute 5 into my function and that'll give me my radius. But the equation models the radius at any point x. Is that okay with everyone? Just looking for some acknowledgement everywhere, yeah? So by summing any value of x in, wherever I am along that equation, that tells me the height at that point. So that would be the radius of the circle drawn at that point. Does that make sense? Yep. Okay, and then the height of my prism is the height of my cylinder. Okay, so if I make a cylinder, then I'm going to call my height delta x. Yeah? Okay, and so that will give me the volume of a disk. So if I want the volume of all of them, then that's where we're going to get to the point. Okay, so this is what I'm talking about here. So you'll notice it's got delta x, that's just the other symbol for delta. Okay, so this symbol for delta is often used when we've got very small values of d, of change, very small changes in x. Okay, so that's what that symbol represents. So it's very small, that. Okay, so it is also the symbol delta, uppercase, lowercase situation. Okay, so when we've got very small widths, okay, and then when we convert that into an integral, that delta x, so as we let delta x actually become 0, or approach 0, then the delta x becomes dx. There's my function, my area formula, pi times the radius squared, and we're going to sum them up between a and b. Okay, so the limit, as we get very small, that sum becomes the integral, which is where we've got that formula. So then we end up with our formula for the volume of rotation around the x-axis. Okay, repeating, that is our formula for the volume of rotation around the x-axis. Now I have got it summarised just here. I need to make it a bit smaller. Okay, so there's the summary of the two. Now we only talked about the x-axis so far. Okay, but hopefully you can imagine that if I rotated around the y-axis, the same idea applies. Okay, except the radius is now going to be on the y-axis. So I'm integrating with respect to y. And our radius is going to be along that way, the x-axis. Because our cylinders are that way, are horizontal rather than vertical. So I'm just going to give you a chance to jot those down, and then we're going to do some examples of applying this. This is one of those really nice applications of integration that's used in reality. You want to create a 3D object, 3D printing uses this sort of calculation. All right? For example, amongst a massive lot of other things. Excuse me. You're not going to get multiple choice questions on the just let me know. But I've given them here because at least you can still be asked like that question, but it's just one of the answers in front of you. That's correct. I'm not allowed to given multiple choice questions on I1 or I2, which, I2 or I3, which is your internal exam. You can only get them on your external. You will get them on your external exam in year 12. Yeah, same for science. Okay, so what we've got here, just to reiterate, you'll notice that in both formulas, the pi's out the front because pi's a constant. We can take coefficients out the front. Just don't forget it's there, because I can't tell you the number of times I've done the calculation and wondered why I'm out. It's because I've forgotten the pi. The other thing that I quite often forget to do is square the function. I'll remember the pi part, but forget to square the function. That's annoying. Okay? Really annoying. So they're the errors that I tend to make with this. I either forget the pi or I remember the pi but forget to square it if I make an error. So let's have a look at some examples of where this might work. So here's example number 1. So I've just got the formula, just a nice easy one. So sketch the graph of y equals 2x. That's about as easy as it gets. And identify the region bounded by the graph, the x-axis and the line x equals 2. And then calculate the volume of the solid revolution when the region is rotated about the x-axis. So nice, simple example. Hopefully. All right, let's have a look at this question. So we're going to sketch the graph of y equals 2 to the x, praying to all that is holy that you didn't have any problem drawing that line. Okay, y equals 2 to the x. Okay, so if we're going to rotate that around the x-axis, then it's going to look like that. Okay, so we're looking for that volume there. Even though it's a straight side, it's still going to make a circle. So our formula for the volume is going to be equal to pi times the integral from 0 to 2, because it tells us it's going from the area bounded by the graph up to the line up to 2. So there, f of x squared dx. Okay, so we're going to have pi times the integral from 0 to 2 of 2x all squared dx, which is that. Okay, again, the key is remembering to square your function, because that's the radius squared for our calculation. All right, so we're going to have pi times, so that's going to be 4x cubed on 3 between 0 and 2. So we're going to have, so 2 cubed is 8 times 4 is 32, divided by 3. So 32, God, I'm glad I don't listen to you sometimes. 32 pi on 3 units cubed. If you have a look at that formula, by the way, okay, ignoring the 0 to 2 part, okay, 4/3 pi r cubed. Mm-hmm. Because that's what you've created.
Oh, right. That's cool. So that's where it comes from?
Yeah, that's where all those formulas for volume come from.
No.
This. Okay, so that was, so we, do we...
That's why you don't explain it to us in
Yeah,
primary.
exactly. All right, so are we okay with that? Yep. So the reason we do pyramids and prisms is we show you the volumes of 1/3, but we don't tell you other than that. Okay, so try a different one. Okay, so same idea, sketch the region bounded by the curve y equals ln x this time, the x-axis, the y-axis, and the line y equals 2. So draw that line first. So draw question A, and then I want you to read question B very carefully before you launch into it. Okay, read question B very carefully, and then have a crack at it. God, I hate times it's two completely different topics at the same time. All right, got to get my hand to that. I'll come back to it in a sec. Okay, so have we graphed ln x? Okay, so looks like this. Okay, so graphed ln x. The x-axis, the y-axis, and the line y equals 2. The line y equals 2 would go through here. Okay, so y equals 2 is there. Okay, and we're rotating around the y-axis. Okay, well, so if we think about the volume around the y-axis, we're going to go from A to B. Oops, got the pi already. Then we're going to have f of y squared to y. Okay, so I need a function in terms of y.
Rearrange y, is that right?
Yeah, so exactly. So y equals ln x becomes x equals e to the y. So I'm going to integrate, and what are we integrating between?
0 and 2.
0 and 2. Okay, so we're going from the y-axis up. So we're looking at this area in here. Right, that's the area we're interested in. So we're integrating between 0 and 2 of e to the y squared to y. Okay, so that's going to be pi lots of e to the 2y over 2 between 0 and 2. So we're going to have e to the 4y, e to the 4, sorry. So pi lots of e to the 4 on 2
Minus pi 2.
minus pi lots of e to the 0 on 2, which is pi on 2. Yep, so you're going to have pi on 2, e to the 4 minus 1. Units cubed. Because we're doing volume. Make sense? Yep, so this is one of those situations where you're given the function in terms of x, which is normal for us, but because we're rotating that way, okay, we need to make sure that we express our function in terms of y and integrate that, and these values here must be y values, because we're integrating that way. Okay, so last example before I give you some to try. So a practical example. So a drinking glass is a base diameter of 5 centimetres, a top diameter of 7 and a height of 11. Now obviously I don't want you to just use your volume formulas, I actually want you to think about this in terms of volume of rotation. So I want you to use integration to solve this problem. You have to make a bit of an assumption, but that won't kill you. Okay. I'll leave you to have a think about it and try and solve it using volumes of rotation.
It works.
Okay, so if you haven't already started this one, there's two ways you can do it, but what I would probably do is turn the cup on its side. Right? So if I was to do this, I would say that distance there is 11, right? Then that starts at 5 and goes up to, it would be 2.5, sorry. 2.5 there, and that would be 3.5, right? And then I'd have a line like that. And then if I rotate that around, I've got my cup. So I need to find the equation of that line. Which is not hard, it's just a line. So have a crack at that, and then I've got a couple of other examples over here on examples 2. Have a go at both of those. All right. So this is examples 1 we just did. Have a go at examples 2, and then we'll continue this on tomorrow. Is that question 9, girls? Is that question 9? Yes. All right, I'll get it sorted for you. I'll try and work out.